Okay, so the big idea here is can this cork really go in a flat circle? Which if we look at this, we'll get the tension along the string. Sorry, I'm not very good at drawing with this tablet. And then you have the weight going straight down. Well, there's no problem with the tension going towards the center because that's fine. It goes in the middle of the circle, we get the centripetal force. But if mg is pointing down and there's nothing opposing that downward motion, then according to Newton's first law, if there's an unbalanced force, it should move in that direction. So really, what probably happens, regardless of whether you try to make it happen on purpose or not, is that the cork sinks a little bit. So you get the mg that's straight down, and then you get this tension vector along the string, which we can break into x and y components. Well, I can't get that thing to go away. So here's tx, and here's ty. And I have to be a little bit careful because they said that they're going to swing it at 60 degrees from the vertical, and we usually measure from the horizontal. So this angle down here, I would mark it as 30 degrees. That right there is going to be 30 degrees. Alright, so part A, I can't remember who's who, but basically the good thing she says is that we should spin it at an angle. And that's so that you could use components to find that ty and mg are balancing each other. Your cork wouldn't be moving vertically. And then tx we can figure out as long as we know the angle. So that's a good thing, to spin at an angle. In fact, you have to. The thing she says that's not good is about trading people who are spinning the cork. And that's because if you have different people spinning, you're going to have more variables introduced into your system. So this is effective and this is going to cause errors. And so you need both of those. 1 point for the good thing with an explanation, 1 point for the bad thing with an explanation. For part B, the good thing that she says is to increase your revolutions from 2 to 10. And that's so you get a better average. It's hard to swing something at a constant velocity, and so the more revolutions you have, the better your average is looking at the real period of the time it takes for it to go around. The thing that she says that's not great is to try to keep it at the 90 degrees. Troy, shh. Okay. And that's because it's just flat out impossible. We can't really do that. Let's see. I'll have to look at the problem to see what's the other questions. Okay, so part C was saying, can it swing in a flat circle? And the answer is no. We've talked a little bit about that. Part D was a little confusing how it was written. So there's a couple things that I would accept on this problem. Really, what they wanted you to do is say that at point 3, the velocity is tangential, pointing to the left, the force centripetal is pointing towards the center, and the acceleration is pointing towards the center. Some people were not sure if they meant like a single point or if they were talking about the entire circle. So really there's 3 points on this problem, and I was looking for 1 point showing that you understand that the linear velocity at any point in time on the circle is tangential. And you either use this vector to talk about point 3, or up at your diagram you drew a tangential vector everywhere, or in a sentence you somehow said that. And then the other 2 points, 1 point for saying that centripetal forces point towards the center of the circle, and that acceleration, centripetal acceleration, points towards the center of the circle. So because of the way the problem was written, there's really a couple different ways you could get those 3 points, either using this diagram, using point 3, or just describing in words what you were trying to say. Okay, for the last part, they actually asked you to solve for I think the tension in the rope or the centripetal force, something like that. So basically what you're going to do is the sum of the forces in the x, which in this case is a centripetal force, equals MAC. and you're going to have the sum of the forces in the y equals MAY. So over here in the x direction you end up with Tx equals mv squared over r, and over here you're going to get Ty minus mg equals 0. So Ty equals mg, and Ty can be written as T sine 30 or T cosine 60, depending on how you drew your picture. Over here you get T cosine 30 equals mv squared over r. And of course at this point it's a simultaneous equation, so maybe over here solve for T. T equals mv squared over r times cosine 30. We plug in and we get mv squared over r, and I'm going to write this part as sine 30 over cosine 30, because sine over cosine is tangent, equals mg. Cancel our m's, and then I can't remember what we're solving for, but basically you can solve this equation, you know everything but one thing, and then you could plug that back in to another equation if you're looking for the force. So that is the second problem.